Hi everyone, in this video I am eventually going to get to section 4.3, but first I just wanted to double let you know that we will not have a skills check this week. So I originally had it on the calendar and then I stated it in the last video. I was able to delete everything from Canvas, but I didn't want to re-record the last video, so just so you know, there is no skills check this week. I think we'll have enough work with 4.3, 4.4, and 4.7, and I also think we'll have a lot of practice between the homework and the handouts from the section. So wasn't too worried about doing another skills check, and I wanted to take at least a little bit of the workload off. Okay, so now let's go ahead and dive into section 4.3. In section 4.3, we'll think about how derivatives affect the shape of a graph. This is going to be a continuation of section 4.1, so in order to start on 4.3, need to make sure remembering a few things from section 4.1. All right, so first remember from, and this doesn't need to say sections, it can just say remember that. So first, let's remember that a critical value, so a critical value is a value that occurs right at the x place or the x value where the derivative is either undefined or 0. Okay, and of course, if we're in class, I'd be asking you if you remember these things, but I'll just tell you. So the second thing we learned is that a critical point occurs at the xy coordinate. So you have an actual point where the derivative is either 0 or undefined, right? The absolute minimum occurs at the lowest y value, or you could say the lowest f of x value, and the absolute maximum occurs at the highest y value, or you could say the highest f of x value. Right? We also learned that graphically we can have local minimums that look like this first picture. So we see we have a c there. The first derivative here is of course 0 because the tangent line is horizontal. Right? Some terminology we can use for this figure is what we call concave up. So if you see like a U, something facing up, almost like a little parabola, or that shape starting to take form, we call that concave up, right? If it's an upside down U, we call it concave down. So in this image, we have what we call concave down. So we know we can get these max and mins. Okay, so far these are just max and mins when we have the derivative at 0 or the derivative being undefined. What we haven't talked about yet is what we call an inflection point. So we can actually have critical numbers or critical points that are not maximum or minimum values. So we didn't have to deal with any of those in 4.1. Now we're saying, this is actually important. We should look at it. So when we have critical numbers that yield areas in the graph that are not local max and mins, we may have what we call an inflection point. An inflection point. Okay, so an inflection point occurs when our graph goes from concave up to concave down, or vice versa. So we could also say from concave down to concave up. In other words, this happens when there's a switch in concavity. When there is a switch in concavity. Right, and one thing to note is that the first derivative does not have to be 0 or undefined. It wouldn't be undefined, but it does not have to be 0 for this to happen. So that's the weird thing in here. You can have inflection points in areas where the first derivative is not 0. So, for example, if we look here, I'll do this in 2 different colors. Notice that here, this little part, whoa, that's not what I wanted to do. There we go. Okay, so this little part, if I sketch it out in blue so you can actually see it, there we go, sketch it out. This part is concave up, so you can see it sort of starts to U up, so that's concave up. Now, the second half of it is concave down, concave down. So since this switches from concave up to concave down, this is called an inflection point. Since we have this flat horizontal line right here, meaning the tangent line is horizontal, we know our derivative is 0. Right? This image got messed up because I just did that weird thing with the computer, but I'll try to resketch it. So right here, there we go. Right, this part is going up, 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 but it's concave down because it loops down like this. Try to redraw it in there. Then we have that flat tangent line. So you can see the derivative is 0, right? And then when we go here, it switches to concave up. So right here, we have an inflection point. The odd thing is we don't necessarily have to have the derivative being 0 to get an inflection point. So here we see this is concave up, right here in blue, right? Then it switches to concave down. Here in pink, it loops down. But where this point is, it's clear that the tangent line is not horizontal, so the derivative is not equal to 0. Right? Coming to the next one, we go from concave down right here, so concave down, and then it switches to concave up, but we can see that the first derivative is not equal to 0. So the question is, okay, well, how do we tell exactly where we have these points are? How can we use the first derivative or even the second derivative to figure out if we have a max, min, or an inflection point? The way we do this is we use what we call the first and second derivative tests. All right, so you don't always have to use both tests, but both have their own good uses, which is why we're going to cover both. In this video, I'm just going to cover the mechanics, or I guess I should say the reasoning behind both of them. In the next video, I'll show you an example so you can see how it all, works together and plays together. So, in general, the first thing we're going to do is calculate all critical numbers. This is just like section 4.1. It's the same technique as section 4.1. Right, after you do that, you create a number line and put those critical numbers on it that you found. And then you're going to also put anywhere where the function is undefined on that number line. And you'll see why we do this and what I mean when you see a computational example. Right, after that, you're going to perform what we call the first derivative test on the number line to figure out if you have a max, min, or an inflection point wherever you found those critical points. Before we can go through and do this, we have to remember a few things. The first thing you need to recall is that if the first derivative is positive, the function is increasing. Right? If the first derivative is less than 0, aka negative, our function is decreasing. If the second derivative is positive, we actually talked about this. Oh no, we didn't talk about this. Just kidding. If the second derivative is positive, let's see what happens since I don't think we've specifically talked about this. So let's sketch out a function. Alright, I'm going to call this my function f. And let's say it looks like this. A little u up, and we should remember this is called concave up. This is c. Alright, now let's use our memories, hopefully, from section 2.8 and draw a first derivative of this. So f prime. Okay, so remember from 2.8, we take note of where the tangent line is horizontal, which is at c. Right, notice on the left-hand side of t, my slope, sorry, of c, my slope is negative. So I have a negative slope. On the right, it's positive, so positive, and again, this is just a sketch, so obviously it's not perfect, but it gives us a good idea. All right, now what I'm going to do is look at the second derivative. Okay, what does the second derivative look like? All right, so, oops, not f, just f double prime. Right, so here we should notice in the first derivative that the slope is positive the entire time. Now remember, the second derivative is really the slope of the first derivative. Therefore, we know the second derivative is positive. Don't know where that little line is, but I do know that it's positive. So here, if f double prime of x, so our second derivative is greater than 0, aka positive, our function is concave up. Right? And we could use similar reasoning to show that if our second derivative is negative, aka less than 0, our function will be concave down. Alright, so now that we have that background information, let's go over the first derivative test. Okay, so with the first derivative test, if the derivative changes from positive to negative at point P, so at some critical point P, which is specified up here, then f has a local blank at p. All right, let's think about this. Our slope changes from positive to negative at some point p. We should see that we're going to have a local max there based on that picture. All right, next, if f prime changes from negative to positive, so the slope goes from negative to positive, we should see that we have a local minimum. All right, finally, this should say if f prime doesn't change, meaning it goes from negative to negative, negative to negative, or from positive to positive, we actually have what we call, or what we've talked about, as an inflection point. Inflection point. Right, so let's take a look at this visually. Okay, our slope goes from negative, then we have a critical point, and it goes to negative. This is P. We can see that that is an inflection point. It goes from concave up to concave down. Now, if this goes from a positive slope, and then we have a critical point to a positive slope, then we can see we do have an inflection point because it switches concavity. It goes from concave down to concave up. Right, so the first derivative is useful for doing this when we have that critical point that we identified by taking the first derivative and setting it equal to 0. However, we have seen from up here that there can be inflection points when our first derivative is not 0. The second derivative is what's going to help us catch this. So this is where the second derivative test comes to play, although sometimes it's more efficient to use it to classify max and mins as well. So you can still use the second derivative test to classify max and mins. I'll show you what that looks like. Okay, and then I'm just going to say C above because we just talked about that, which is what I scrolled up to. Okay, so the second derivative test is going to catch more inflection points than that first derivative test. Okay, so first things first, if f prime of p is 0, that means we caught that critical point with the first derivative test. If we want to, we could take the second derivative. So if at that point p, the derivative is 0, and f double prime of p is greater than 0, we talked about that up here, f double prime of p is greater than 0, our function is concave up. Okay, so that would mean that we have a local minimum. Remember, because it's concave up, so you'd have a local minimum. Right? If our second derivative is less than 0, remember from above, that means we have something that's concave down, so we get a local maximum. Alright, what's a little bit odd is if you have a second derivative that is equal to 0, it is inconclusive, and you have to actually go through and test it with the second derivative. Okay, so if you find f double prime of p is 0, then you have to figure out what the second derivative on the left-hand side of it is and what the second derivative on the right of it is. If your concavity switches, goes from positive to negative, or negative to positive, then you have an inflection point. Alright, so here, so you go through and you find this. Okay, looks like this. F double prime of p is 0 right here. Right, we see this part, green. Well, it's supposed to be concave up. My drawing's not that great. Right, this is concave up, so you know that f double prime of whatever point you take up here is going to be positive. Right, down here, this piece, okay, it's concave down, so f double prime would be negative. Right, so the idea is if you get f double prime of p as 0, if the second derivative is positive on the right, it's going to be concave up. negative on the left, concave down, there is in fact a switch in concavity because it goes from negative to positive, so you know for sure that you have an inflection point, and this works vice versa as well. So if, say, you did this, this is concave up, so F double prime is positive, case switches to concave down, and that's not supposed to be that flat. This isn't supposed to be 0. It's not really. Okay, so this is F double prime is 0. Right, and here we have F double prime less than 0. So flip-flop the drawing, but you still see it goes from concave up to concave down, and you could go vice versa. You could go from concave down to concave up, draw the same conclusion. The point is, if your second derivative changes from positive to negative, or from negative to positive on either side of that place where F double prime of P is 0, then you know you have an inflection point. If it doesn't change, then you wouldn't have an inflection point. Okay, so that gets us to a lot of their reasoning. In the next video, I'll do a computational example. I just wanted to break it up a little bit. And the computational example will be somewhat long because it's going to put together all of these concepts.